You guys good to go? Okay, quick recap of yesterday before I start on today's new notes. Yesterday I probably shook your worldview, like literally, because I told you north is up and south is, no, north is down and south is up. Okay? Magnetic fields are arbitrarily defined as whatever direction the north end of a compass needle would point. Which means that north does not actually point north, because north things, north things are actually going to be attracted to south poles. Does that make sense? So that when we say that, I'm using my fingers here, quote, the north end of a compass is pointing north, it's pointing geographic north, but it's not pointing magnetic north. That makes sense? Which is very, who thought of this? Who didn't, well, maybe a better way of putting it, who didn't realize that this was going to cause a problem when we taught it to physics kids years later? We're going to have a very similar problem today. What the heck?
Yeah.
It's not that, but... Okay, so the problem we're going to have today is about current. Hi. Okay, so what I want to talk about today is when we work with moving charges, that's our topic. Moving charges is basically like the definition of current. Current usually, though, would be like electrons moving. That makes sense? Like when you have a wire, electrons move through a wire. So convention would be that electrons are going to move from negative to positive. Does that make sense? So whenever I draw like a battery or something like that, like in say this particular picture right here, the electrons would be going from negative to positive. Does that work? That would be called electron flow. This is where this gets stupid. If we use the term conventional current, which you might think, oh, conventional current, that's the same thing as regular current. Conventional current, for some reason, was defined as the way positives would flow. Even though positives don't actually flow, because positives are found in the nucleus, and nucleuses don't move. Does that make sense? So what we're going to do today is talk about everything twice. Once for what would happen if electrons were moving, which is what probably is happening. And then we'll talk about it also for what would happen according to conventional current, which would be if positives were moving, which they probably don't. Yes? That's actually what I learned when I was your age learning physics. It actually gets brought up a lot, surprisingly, which makes no sense because, you know, from a physics point of view, we should talk about electrons moving. But no, it actually does. This is one of those really frustrating lessons where it's kind of like north is south and south is north kind of concepts here. I wish we could just go back and just be like, let's just rewrite science history to make everything nice and straightforward. So okay, let's give this a try. There's an experiment I want to start off with. Hans Christian Ørsted basically messed around with compasses and electricity. This is like the link between magnets and the previous section on like electric charges, and discovered there was a relationship. He discovered that there's a perpendicular current. It's going to induce a magnetic field. Okay. So I want to show you the video first, I think. Just going to skip ahead to where that was. Here it is. Let's start with this.
In 1820, the Danish chemist and physicist Hans Christian Ørsted performed a celebrated experiment demonstrating that an electric current passing through a wire could deflect a magnetic needle. The experiment can be reproduced by means of the following apparatus. A wooden base carries a magnetic compass. A brass frame above the compass holds a thick copper wire with a small clip at each end. A pinion is used to raise and lower the wire above the compass needle to determine the relationship between its deflection and its distance from the wire, through which an electric current flows. 3 leveling screws ensure that the system is perfectly horizontal. After arranging the device so that the magnetic needle is parallel to the conducting wire, the 2 ends of the wire are connected to the electrodes of an array of batteries, and a current is sent through it. We observe that the needle deflects towards a position at a right angle to the direction of the wire. When the direction of the current flow is reversed, the needle still tends to deflect toward a perpendicular position relative to the wire, but this time its poles are reversed from the previous position. In a similar experiment, Ørsted demonstrated that a continuous electrical current flowing through a conductor generates a magnetic field. He was thus the first to prove the interdependence of electricity and magnetism.
That makes sense at all? Basic idea is he hooks up a wire, and he puts the wire like parallel to where the compass is going to be, I guess. Really, he should have done like perpendicular maybe. We'll talk perpendicular in a second. But sets up a wire, okay, and then he puts a charge through the wire. Normally the compass would point this way. He turns on the like electricity, and the compass, like north is that way, and the compass all of a sudden does this. So what does that mean? Well, it means that moving electric charges actually emit a magnetic field. Say that one more time. He discovered that moving electric charges emit a magnetic field. Because why else would the compass move? Right? What is a compass supposed to do? Well, it's supposed to point towards South Pole. Yes, good job. The compass should point toward the South Pole, right? And so if normally the compass was pointing this way, and then right next to you have a wire, it's going to all of a sudden emit a perpendicular field. So you know how they were parallel? The perpendicular field is going to cause the compass needle to point this way now, which is now perpendicular. Does that make sense? This is really annoying. Don't show this message again. Okay. One of the words I want to use here is the term induces. What he basically discovered is that the wire and like the wire that he was working with is not actually a magnet, obviously, but it functioned as though it was a magnet. Does that make sense? So what ends up happening here is there's actually like fields going in a circle around this wire. So I want to try to explain that over the next few slides. Before I do that though, I want to discuss what current is, just to make sure we're clear on this. Current and voltage are different from each other. And a common like misconception kids might have when they're starting off with is they think they're the same thing. So a quick reminder about both of them. Current is the flow of charges. It's typically electrons in a wire. Okay? Current is measured in what's called an amp or ampere, and that's a coulomb per second. What's a coulomb? How much charge there is, right? So an amp is how fast that charge is moving. Does that make sense? Right, like if one thing of current has 15 coulombs per second, but another one is 12 coulombs per second, well, one of them is moving like there's more charges moving per second, right? So essentially it's moving kind of faster. That makes sense. That's what amps are, which is current. This formula here came out really blurry. It's on your data sheet. This is I equals Q over T. I'm going to make that like a capital I. Just to make sure we're clear there. What's voltage then? Well, voltage formula is the change in energy divided by the charge, I believe. Is that the formula on your sheet? So voltage is similar, but it's more based on how much energy something gains. So it's based on like distance between plates. So like voltage measures the differences in energy. I had an analogy before. Maybe I should talk about that one again. It was like, imagine you've got like one of those like water tanks that you'd like put up way up high. If that makes sense. And then like there's a little hole in the tank. Okay. Let's say water starts to drip out. Like just little drips. Is there a lot of current to that? Let's say no. How do you increase the current? Rip a big hole in the water tank. And water comes gushing out very fast. That's current. That makes sense? Voltage is how high it is off the ground. So this water has from here to fall. But if the hole was up here, it would have from here to fall. Does that make sense? And so one would have more energy when you're done. Okay. Here's my talk about conventional versus electron current. This is, like I said, it's stupid. I wish we could go back and just rewrite it because it's going to confuse physics kids for, you know. But here's the concept. Electron current is the direction that electrons travel. If I talk about conventional current, though, it's talking about the opposite of that, which would be like the direction that the protons are traveling, which, granted, they're not really traveling, but you know the term like relative motion? Relative to the electrons, the protons are actually moving. Does that make sense? Like if you consider that the electrons are stationary, which they're not, but if you think that they are, then compared to the electrons, the protons are moving. Does that work? Okay, so what we're going to do today is talk about a lot of different rules for figuring out how these moving charges inside like a wire, for example, how they make magnetic fields. I'm going to talk about 3 different rules. Typically they're known as the left-hand rules. Left-hand rules are for if you're talking about electrons. Right-hand rules are for if you're talking about protons. I put a little note here. You can always tell when someone is working on the magnetism unit on their tests because they'll be doing all sorts of weird stuff with their hands, trying to like orientate their hand to make it work. I'll show you. Like you'll get what I mean when we're done today because you're going to be like going. So. Okay. Oh, sorry. More conventions before I even start. Sometimes we actually need to have stuff going like not up and down and side to side, but we need to add the 3rd dimension of like in and out of the page. So convention for that is a dot means that current is flowing towards you, whereas an X means current is flowing away from you. So I found this picture to help maybe recognize it. Imagine an arrow. The point of an arrow means that the arrow is coming towards you, whereas like the cross on the back of the arrow's, whatever you call that thing, it means that the arrow is going away. What did you say? The quill. Okay. Is that what it's called? Okay. I'm not an archery person. Okay, here's your first hand rule. Let's say you set it up so that you have a wire and the wire has electrons flowing through it. So which ways do the electrons flow? From negative to positive. So if here's your battery, electrons are going to flow from the negative to the positive. That makes sense? What Oersted discovered is there's actually a field forming like circles around the wire, like this. So it's actually perpendicular. The wire is going right up and down, and the field is actually going to deflect the magnet compass like this way. Okay? And so this field right here, the field direction, like the way that we point the field, is based on the way like your left hand fingers would work. Okay. So what you're going to want to do is take your left hand, kind of like I've changed this diagram right here, I put it up and down. Take your left hand. If the current is going up, that's your thumb. So your thumb is the current going upwards. That means that your fingers tell you which direction the field is, which in this example here would be like clockwise. I'm gonna be stupid. Does that make sense? If you were to put a compass right here then, which way would the compass point? It would point that way. And then if you were to put a compass right here, which way would the compass point? That way. And then here, now by the way, this is like flat, by the way, right? This isn't up or down. This is like supposed to be like a flat ring. Does that make sense? So then this one would be pointing like in, like that. And this one would be pointing that way there. As you move the compass around the wire, the actual north end of the needle should move with it. Does that make sense? So the wire is like this, but the compass is flat like that. Hence the perpendicular. Does that make sense? So here the needle would look like that, then it would look like this, then it would look like this, then it would look like that. That makes sense? We're gonna try to do a lab on it on Tuesday, so you guys can kind of test this out. Okay, what's going on in this picture? I pulled a whole ton of pictures off the internet. Is this a right-hand rule or a left-hand rule? Right. Okay, so in terms of the way this one works here, this I right here must not be actually electrons. This must be conventional current. So if that conventional current is going up, then it means that your field would be going this way. So just to make sure we're clear, if you put a compass right here, the needle would point that way. If you put a compass right here, the needle would point. Well, technically that would be like towards us, if that makes sense. Right? If you can visualize this, the wire is going up, and then the circles are going around it like this. So this compass needle would be pointing towards us. In that example. Well, the compass is how you tell which way a magnetic field goes. Because a magnetic field is defined as the direction a compass would point, from north to south. So the north arrow would point that way.
It wouldn't go this way?
Well, the current is going up. The conventional current is going up. Well, it is, but in this case, it's going to be conventional current rather than electron current, which is where this becomes stupid.
So, okay, I'm just confused as to why, like, because the current or the conventional current's going up.
Okay, so maybe let's do it this way here then. Electrons are actually going down then. Okay. So then maybe try using your left hand instead. If you used your left hand instead of your right hand then, and you were to then say electrons are pointing downwards, that's the direction electrons are flowing, then the field is going to go this way around it. So that would be counterclockwise, yeah. From like a downward point of view, a field would be going counterclockwise in circles.
And then, I'm just wondering why that one on the side would be coming towards us instead of just going in the left direction. Because isn't it just like perpendicular and that's...
Well, like this, like it, because it's trying to do it in 3 dimensions here. The wire is going straight up and down, and the actual fields are going like this.
Yes.
So like this guy right here, let's see if I can demo with like my water bottle. This is the current, and then if I put the compass right here flat, like this, the needle of the compass would point that way, towards you. But then if I put the compass out here, the north arrow would point that way. And then if I put the compass over here, the needle would point that way. If I put the compass back here, it would be pointing towards me. So like the north arrow of the needle the north arrow of the compass will be pointing towards me, towards you, towards the door, towards the screen. And so as you move the compass around, there's a magnetic field there. There's a lot of pictures today. Okay. So here's some more pictures just to make, I'm going to beat this to death today. Left-hand or right-hand rule here? Okay, so that means that this picture right here must be the actual, like, electrons are going up. So if electrons are going up, then the field is going to go, like from a top-down view, the field is going to go clockwise.
And the compass would be like opposite?
Well, the compass points the direction of the field. So like north arrow will go with the arrow of the field.
Yeah, you just follow your fingers, go this way, and then they left
So the needle's like the tangent to that.
Yes, the needle is the tangent to that point. Here's an example then. Here's a current carrying wire. Which way will the magnetic field point to the right of the wire? So like for example, if I had a compass right here, which way would the compass point? So first, what does an X mean?
It's going away.
Okay, so current is going in, so you got to point your thumb in towards the board. So that means that the field is going this way around it. So counterclockwise. So if I were to draw the field, it would be like this, 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 this. So which way is the compass needle going to point? Up. Michael.
When we're actually drawing the X's and the dots, are we talking about electron current?
Yes, the X's and the dots should be electron current.
Always.
I don't know that I can say always, Michael. I wish I could. As far as I understood, I wrote this on a previous slide back here. Unless you have good reason to think otherwise, it should be electron flow.
Tangent to it.
Does that make sense? So I would go with electron flow always. That's what seems to be standard in a lot of the newer books. I, though, learned conventional current myself. I learned everything as a right-hand rule. So I want you guys to know both. The thumb is the flow of the electrons. Because you got to make sure you're careful with that.
Shouldn't it be like this then?
And then your fingers are the
The fingers are the direction the field is going to be. So the field is going to be going this direction as you point into the board. So like that's going counterclockwise. So if you put a compass right here, which way would the needle be pointing?
has to be tangent to it, right? So it'd be up.
Yeah, up. Yeah. What was that? Well, because here's where your compass is, and the compass points in the direction of the field. So if the field is going up, the north arrow of the compass would point up.
But if the field was going down, it would go down?
Right. So like if you put the compass over here,
Yeah.
then the compass would point down.
Why are you saying that the field's going up?
Well, like over here the field is going up. Over here the field is going left. Over here the field is going down.
Say we're looking at like overhead and it's like that's like a flat piece of paper and that's just going forward.
Yeah, but that's an X. It's
So the X means it's going into the page.
going into the pit. That's why you did this.
That's why I'm doing this.
Actually, I could have done that.
That could work, yeah. So like on your page do that.
And then that just shows it's like.
That it's going that way around the circle.
How is this case you know if it's left hand or right hand?
Oh my goodness.
Michael asked that one a second ago. If current says right here, I would go with, like my convention would say go with it as current is like electron flow. Unless you have some sort of reason to suspect otherwise.
Okay,
Like if it says conventional current, then go right hand rule. Like I said, this is stupid. Alright. How am I doing so far?
Good.
Is that better? You were really frustrated about 5 minutes ago. Ooh. Oh, he just pulled his nose. That's what that was. Okay, here's a second rule. This rule is for what's called a solenoid. I have an example of one actually. Maybe I'll show you what a real F1 looks like. Okay, this is a solenoid. I'll hold that here so you guys can maybe see. Basically, it's like a long tube, and then this tube right here, there's all sorts of wires running around it. Okay, and so rather than the wires being in a straight line, we're going to curve the wires around it. A very like basic solenoid would be to take like a paper towel roll and wrap a whole bunch of wire around it in loops. Okay, what ends up happening here is it makes what's called an electromagnet. You guys ever heard that term before? If you turn on the current, it's actually going to cause this thing to act like a magnet, where, I'm going to make sure I get this right here. This would be north, and this would be south, I hope. The way this rule works is you imagine that you're grabbing the solenoid. So like imagine that this is sitting right here. Imagine that you're grabbing it like this. Okay. The way it works is that your fingers are the direction of the electron flow now, and your thumb points in the direction of the field. Okay. Which means that if you were to put a magnet right here, the magnet would point this way. Sorry, not a magnet, a compass would point this way right here. But what if you put a compass right here? Which way would it point? No, it would still point this way. Because here, the north end of a magnet will attract to south, and here, the north end of the magnet will go away from north. Michael.
So if you take the wires that you're drilling it up with and you shove it this way with the reversible.
Yep, so sometimes what we'll do then is we'll attach this to a battery. So like if this was attached to a battery back here, right here, this would be the negative and this would be the positive poles of the battery, because electrons go away from negatives and towards positives. That makes sense? If you were to take those wires and then flip the wires the opposite direction, it should cause the compass needles to do a complete 180. We're going to try to do a demo of this on Tuesday next week so that you can hopefully see this in action. I was messing around with it last night. You can see some apparatus over there on the sidewall. Okay, so let's try this here. If this is the electron flow, right here, use your left hand. So the electrons seem to be going over the top and then around and back. So I should be holding my hand like this from your perspective. Then your thumb is the north side of this electromagnet. Can you guys see that? So, like, I like to use my second finger to be the start of this right here. See how this is wrapping around like that? This one's coming over, wrapping around like this. You guys see how that works? So then my thumb is the north side of the magnet.
So the electrons are going.
Well, so the electrons are going here, like from my wrist, through my finger, back up around, through my next finger, back up around, through my next finger, back up around. No. The electron's not towards the south. Like the electron flow goes here, your thumb goes towards the south on this one.
Why does it say north have a solenoid thing?
Sorry, your thumb goes towards the north. My bad.
So the electrons do go towards the south?
Well, oh, I see what you're saying there.
Because it
Like-
says electron flow is going that way, right? So it's going towards the south.
Yeah, because what you're saying is the electrons are going from here towards the south.
That's what I'm really confused.
Okay, yeah, I think that works.
So what?
Because if you were to make the electrons go this way, then it would change it to be that way then. So yeah, I think you could say that electrons are essentially going towards the south. I think that works.
So is it the opposite then?
What is the opposite?
Like what's
Sam was just pointing out that the electrons are starting at the north pole of the magnet. Like the electrons are starting here, going there, up the other side, back around, and the electrons seem to be ending at the south pole. Like in terms of where the electrons start, right? Like the electrons start here, start electrons here, and then electrons are going up this way here, which is like the finish. So they're finishing at the south pole. I think that works. I'm going to check that a few more times just to make sure.
Which way is the magnetic field going then?
Okay, so the magnetic field is going to go the pointing your thumb. Your thumb is the magnetic field, and your thumb is the north side of the magnet.
Okay.
So let's try an example. If you put a compass here, which way would the compass point? Into the magnet, because a compass is a north needle, and north would point to south. And then over here, if you put a compass,
Still point the same
it would still point the same direction because the compass is a north needle. And will the north needle want to point towards the north side of a magnet? Or will it point away from it?
If it didn't already say north and south, would we know by looking at this?
Hopefully,
that
yeah.
It was just that way?
Yeah, hopefully you'd be able to know which north and south was without actually having that written for you.
Oh.
Using the rule. So the rule would be put your hand in the right orientation, and then whichever way your thumb points is the north side of the magnet. One of the cool things about this, by the way, I mentioned this a bit ago, this makes the electromagnets. You ever heard of those before? If you wrap like a big piece of iron in a bunch of wire and you turn on the electricity, it's actually a very powerful magnet. And the best part about it is that when you turn the electricity off, then it stops being magnetic.
Are we going to experiment with this?
I'll see that I can try to find a big piece of iron tomorrow, or Tuesday. Yeah. Come on in. Or don't. Thanks. Hello. You guys can just walk on in, by the way.
She just likes knocking on doors.
Oh.
No, it was locked.
Oh, was it locked? Okay. We're good. We're good. Thanks, guys. Okay, let's try another diagram to make sure this makes sense. Let's say the wires are going this way here. So in terms of holding this, the wires are coming like over the top. So I'd be holding my hand like this.
It tells you which way the field is.
Well, it already tells you, right? So that means that this hopefully confirms it, that my thumb was pointing towards north. Right? Because the back of my hand is the wires going up the top, and then my fingers are curling around the front. So everything's curling over the front, so my fingers would point this way. So that way north is that way. We could actually do a right-hand rule on this one. What if we were to consider positive charges? So imagine that rather than negatives are leaving this way, what if it was... actually, no, this works better because electrons we know are going... actually, this diagram doesn't make a lot of sense. How can you have positives going that way but negatives coming this way?
Is it a conventional?
Well, that doesn't make sense because otherwise you'd have one going one way, one going the other way. Because if negatives are...
They have the negative going around.
Yeah, this should really... Let's not put arrows here instead. Because then electrons would be going this way, right? Like electrons are going to leave the negative and come towards the positive. Does that make sense? So then the electrons are going to be going up the back of my hand, over the top, over the top, over the top. So therefore the field is going this way. Does that make sense? It's going to take some practice, obviously. All right, let's do another one. So the current is going a little differently this time. Here the current is going over, like I gotta hold my hand this way. What's wrong with this diagram? Because I would say you should hold your hand. This is so hard for me to show these guys. So here, the current is going over. So I should be holding my hand this way. Why is this field being drawn the wrong way then? This one must have been implying conventional current for I. This one probably should be a right-hand rule then. Well, I can stand for either conventional current or electron flow, which is what makes this stupid. Like when I was looking up diagrams on the internet, some of them would be going one way, some would be going the other way. I thought, well, let's use that to our advantage. If this is correct, if the magnetic field is going this way, this must actually be conventional current here, where these are going up and over. So the field is going this way. This must have been referring to conventional current in this particular diagram.
Why is the field going that way?
Which hand do you want to use, right or left? Okay, so if we think this is conventional current, well, we don't. That's what we're trying to figure out based on the diagram.
Let's start with left.
Okay, well, how about this? Let's point our thumb this way. Okay, so if we're going to point our thumb this way, are our fingers wrapping around the way that it should be going?
No.
Okay, so therefore this must not be electron flow. It must be your right hand, because if the field is pointing this way, everything is going up and over that way. This I must refer to conventional current in this diagram, not electron flow.
So with that formula, just arrow like that way. It will. That's our first line.
Well, yeah, you know that formula for I is equal to C over seconds? Coulombs can be negative charges or positive charges. Right, because like a coulomb, often we're going to think of electrons, right? But a coulomb could be a positive or a negative charge. So this formula for I could work for positives or negatives technically. Because it was, what was it? It was Q over T. All right, let's try some more examples, see if this still makes sense.
Ah, it tells us. That's beautiful.
Yeah, most of these ones I'm telling you, so I just want to like confirm here. Let's say you wrap a battery coil around here. The electrons would be flowing from the negative to the positive, right? So electrons would be going this way. Electrons would be going this way. Electrons would be going this way. So as I wrap my fingers around, starting from the back side and then around the front, is the north arrow pointing the right way it should be? Hopefully that makes logical sense.
Is this not the same as the last diagram you just had?
This one and the last one? Well, this one, the wires are wrapping from the back to the front. And this one here, they're going from the front up to the back. So that's why this one's a little bit backwards in terms of like where the arrows are.
The arrow. Oh, It is?
Well, you see how these arrows are pointing like upwards?
Yeah. So then the
But then
coil
this
should
one
be
right
going
here, the arrows would be
like
pointing
this.
downwards, I'd say.
The difference is that.
Well, I'm looking at the one right. I'm looking at.
Oh,
the
this one
back.
right here.
Sorry. Yeah,
Okay,
I'm
so
looking
let's
at
do
that.
this one here next then. Is he using his left or right hand?
Right. So then the other one we should have used our right hand on.
So this one is like, if he's using his right hand here, if he's using his right hand here, and this is like, say, conventional current, because you use your right hand for conventional current, which means that these are actually positives going that way. So positives don't technically go that way, so maybe it's better to say that like electrons go that way maybe. If I use my right hand here, and all of the lines are coming over the top of the solenoid, then yes, my thumb is pointing towards north.
Okay, sorry. That's what I was referencing.
Does this one make sense to you then? So as I'm holding it here and all of your fingers are curved up this way, then yes, your thumb is pointing towards north. Which way are the electrons going? The electrons are actually going this way. So the electrons are actually coming up here and coming down here, but because he's using his right hand, we're talking about the conventional current instead.
Okay, sorry. So then this one talking about would be the same as the other one we were all.
This one should be the same as this one here, I think. Yeah,
So this one should have been.
The-
Okay.
the same basically.
Yeah. Okay. Oh, what?
So are we gonna begin through all these notes?
I hope so.
There's still lots of time.
We still got 45 minutes. I don't know. I'll do my best. Okay. Third right hand rule. Okay, this one here is about, let's say you have a moving charge in an external field. So like you have your wire, the wire itself has charge moving through it. So therefore, moving charge makes a field. So like, let's say the charge was going this way here. Using your first rule, this would be like your thumb going kind of into the page. Which way would the field be going? Let's say I'd be wrapping it around it like here
That'd be like the X on the
to
right?
there. Yeah, this is intending to be like an X and a dot there. So the wire itself would make a magnetic field. Does that make sense so far? The wire itself would make a magnetic field. What if you put that wire in another magnetic field? What do magnets usually do to each other? If you have this magnet and this magnet and try to put them together, well, they'll either attract themselves or they'll repel. And that's kind of what's going to happen here is the magnetic field of the wire is going to interact with the magnetic field of this north and south here, and the wire is going to be pushed by a force acting on it. So let me show you this third rule. Let's say you have a wire here, and electrons are going that way. The way it works is that your thumb is the direction of like the electron flow. Your fingers point in the direction of the external magnetic field. And so external magnetic fields always go from north to south. So fingers point towards south. Thumb is the actual electrons themselves. Your palm points in the direction that a force will push things. So this force will actually push things down. Does that make sense? So the direction of your palm is the direction that a force is actually going to apply. Because two different magnetic fields, one based on actual magnets, and the second one based on current in a wire, those two fields will interact and will either cause like a push or a pull kind of thing, right? And so to know which way it's going to go, that's what this rule is for. So your palm shows you which way the force is going to try to push things. It's going to push it down.
The electron flow is the other way, would then be up.
Yeah, so then if the electron flows the other way, you'd take your hand from this and you'd flip it this way, because you're still going to point your fingers towards the south magnet. But then the electrons are going this way, and that would cause it to get forced up.
So this rule with the way like what's the sign with the finger is kind of opposite because the other ones it was like this was field.
Yeah, like
this
it's
was
different every
current.
time.
So this is.
Yeah. It's going to take some practice. Okay, I found a different diagram here, but if you'll notice the hand that he is using his right hand. So nothing changes except now, rather than it being electrons moving, now it's protons moving. You can see how there's a proton picture there. So imagine that the proton was trying to move up, and the field was pointing towards like my left. Which way would the force be? Towards us, basically, is what this is referring to. This is my hand here. If a proton was going up and the field magnetically was going that way, this thing would be pulled towards you. Michael? Yes, the actual wire itself would get pulled down. Or if it was just a single charge, the charge itself would get deflected, which is what I'm going to do in some of these next examples. But yeah, the wire itself will actually get pulled. All right, here's your, what hand is this? Right hand. So field goes this way. In terms of current, this must mean that like positives are going this way. Positive charges are going that direction if you're using your right hand. So then the electrons themselves must be going the opposite direction if you use your right hand. I found this picture. I thought I'd point out, this sucks, doesn't it? Does it make a difference? Like, it's stupid either way. I just need you guys to be able to handle the whole positive negative thing and know how the 3 rules work. Okay, let's see if I can explain this next diagram here using that 3rd rule here. Let's start with the negative charge. If the negative charge was going this way, that means that you'd use your left hand, and you'd point your left hand like that. Then you're going to point your fingers towards the south pole. What will happen is
Mr. Bonnet, please come to the office.
the charge will go down.
Mr. Bonnet?
So if it was a wire, the wire itself would be forced down. If it was just like an individual proton, the proton would get pulled downwards. Whereas if it was a positive charge, use your right hand. The right hand would imply that I need to have my thumb go the direction it was trying to go, so like that way, still pointing towards the south pole of the magnet. A positive would get deflected upwards.
Which makes sense because you're opposite.
Okay. You need to answer a lot of different theory questions based on that. So I'm going to try to find you as many as I can to help. And obviously you can see why I printed off like a million pages of textbook stuff to read. Because it's tricky. Yeah. There are 2 formulas you need to know. You're probably going to like this better because the formulas are pretty easy in comparison. More or less easy. So here's 2 formulas. And these are, by the way, both for that 3rd rule. Okay. So if you have current running through a wire and you want to find that force, we can find that force amount. Or if you just have a charged particle, we can find that force amount. So we can either do it for like an actual wire or just like an itty bitty like 1 particle thing. Okay. This is really confusing though. The first one is I, which stands for current. And the second letter is L, which stands for length. And here's where it's dumb. They use an I that has like just a line. And then they use an L, which is just a line. Again, someone should rearrange physics and make it smarter. And then this last thing here is B. This one right here. That one's B. And do you remember what B stands for though? Magnetic field. Magnetic field. In this particular formula, Q stands for the charge. So it could either be an electron or a proton. But like we're talking just like one individual particle. And then v is going to be its velocity. And then b, again, is how strong the field is. You have to use the right formula in the right place. So let's try an example. You have a piece of wire. Yeah. Okay. So the magnetic force you're looking for would be equal to the current times the length of the wire times the magnetic field. We have like 3 out of 4 numbers, right? So this is 1.884 newtons. The current, we don't know. We're looking for current. The length of the wire was 345. And the magnetic field strength was 129 Teslas. After what we just did, this is going to be a lot easier. Just divide up those 2 numbers and you're good to go. Yeah, this should probably be like a 0.25 maybe. Get a calculator. I don't have any calculators nearby. There we go. Okay, so I got 0.42. Actually, I need 3 sig digs. 0.423. Current is either going to be defined as a coulomb per second, because that's how fast the electrons are traveling, or sometimes they call it an A, which stands for an amp. An amp is a coulomb per second. Yeah. Does that work? Look forward to the math questions sometimes. Okay, it is possible for them to not have these things be at perpendicular angles, because ideally what you should have is a field where they're going like perpendicular to each other. If they're not, there is one little twist. You just throw on a sine theta on the end. And the theta is the angle. That's it. So I don't think they're going to give this to you on the diploma. What are they doing?
No, banging on the wall.
Holy smokes. Can you guys knock that off, please? We're trying to do stuff, and it's tough enough as it is. This is a tough lesson. All right. Okay, so same thing here. The only difference is throw in the sine of 67. That's it. So 1.884 equals a current we don't know times a 345 times a 129, but then times it by the sine of 67. I doubt they're going to give this to you. I don't think they're going to give you like an angle there, but like I said, I just want to make sure I'm thorough. So in case they do, it's the same formula, but with just a sine of whatever angle it is. So.
It says
Yeah, make sure you're in degrees in your calculator. I got 0.460. Wait, I only get 2 sig digs now. 46 amps. Did you guys get 0.46? Like I got 45988.
Yeah.
Okay, so only 2 sig digs though because of the 67 degrees now. Does that make sense? Okay. The reason why we don't normally use this section right here is ideally you should be given this thing when it's perpendicular. Perpendicular would imply 90 degrees. Do you guys remember what sine of 90 is though? It's equal to 1. So typically you're going to be asked a 90-degree perpendicular question. That's the symbol for perpendicular, by the way, an upside down T. So we don't usually need that. Does that make sense? Do you guys want to take a break now, or should I just finish off the last examples?
Let's just finish. There's only like, oh, maybe not.
Yeah, we want a break.
Okay, let's go take a break because it's been enough as it is.
My butt's starting.
Okay, we'll pause for 5 minutes here. Okay, I got 4 examples left I want to try. So I started drawing a bit of a diagram for this first one. Hopefully this makes sense. You've got a charge coming out of the page. So I drew it with like a dot right here. I kind of tried to draw a bit of an arrow here to imply that this is going to be coming straight towards us. Does that make sense? The length of the wire that this charge is flowing through is 3.6 meters. And there is a force that's going to try to push the wire up. So first thing I want to do is I want to use our last rule, the hand rule, and try to figure out which direction the magnetic field is. I'm going to go stand in front of the board here. Okay, it's a positive charge. Right hand or left hand? Okay, right hand. The charge itself is coming out of the page, so my thumb has to be coming towards you. And then the other thing I know is the force itself is going up. So like that. Yeah. No, that's really awkward. Does that make sense though? My thumb is coming out of the page.
Yours perfect.
My thumb is coming out of the page. The force is going up. Which way is the field pointing?
This way.
That way. So, right. Alright, so first thing we know then is that the field itself is going that way. So the field is going to be going right. Maybe if I were to draw magnets, this would be like a south end of a magnet. And this over here would be the north end of a magnet. Does that make sense? So the field is going from north to south. Second thing I want to do now is figure out the actual strength of the magnetic field. So that's just using that one formula. So it was like magnetic field strength is equal to current times length times the B value. And that's what we're looking for. We're looking for B.
Aren't we using the charge one? Velocity?
Well, no, because this is a wire.
But it gives us coulomb and meters per second.
Yeah.
We don't have meters.
Well, we have meters and seconds.
Okay. It's going to be similar here then. Because it's a wire though, we still want to use the length. Remember what I equals though?
C over, oh. So
Coulombs over second. Like a current, it's a charge per time. So your force is 235. Your current is 2.6 in the 6.25 seconds. And then your length is 3.6. And you're looking for B. It's going to kind of work out the same way though, isn't it? Because this right here would be a velocity. And that would be a charge. You know what? It would have worked both ways. It's good though. So. So you need what? 235 times 625 divided by 2.6 divided by 3.6. How many sig digs do I get? Just 2 sig digs?
it was just rounded a little bit differently. What did you get?
I got 1.569. So 1.6, and then the unit for field strength is Teslas, and then this would be going right, at least based on our diagram. Yeah, we're gonna have to figure out which direction fields go, like left, right, up, down.
Just for fields? Or
For fields, yeah. Well, force as well, like force will go up, down, or something like that.
But no, for like currents, right?
No, current doesn't really have a direction to it.
So round it down, and then just round it up.
So the other, wait, so this formula is for a wire, and the other one is for what?
This one's for a wire. This one's just for an individual charge, which is what we're going to do on the next examples. So let's just say you have just a particle going through a field. How much force will it experience? So this is the other formula. A magnetic force is equal to the charge of your particle times by your velocity of the particle times by your field strength. So an alpha particle is 2 of the elementary charge. And then your velocity is 1.22 times 10 to the 4. And that's a really strong field. We're solving for force. So just, in case you missed that, the alpha particle is 2e. So it's 2 times 1.6 times 10 to the minus 19 coulombs. That's the charge on an alpha particle.
Don't we have a direction on this too?
Yeah, we should have a direction. That being said, I didn't really give you the I didn't give you enough information though to know which way the field was going. Because like I'd have to tell you which way the particle was going. I'd have to tell you which way the field was going. So why don't I? Well, so I mean, alpha particle means use your right hand, but I didn't tell you which way the particle was moving, like left, right, up, or down. So I probably should have said like what magnitude of force does it have? Because you're right, I should probably give you more information for directions otherwise. Power 4 times 23. I got 8.97 to the minus 14. So yeah, 9.0 times 10 to the minus 14. And this will be a Newton now, because we're talking about force. Does that work? Okay. Okay, 2 last examples. This, I'm kind of feeling like you should expect to get a question like this for sure. Because it's going to combine it's going to combine this unit with dynamics. Okay. Let's say you have an electron moving through a field, and the field itself is into the page. Okay. So if I were to have my hand rule going on here, the electron itself is going right, but the field is going into the page. Which way is the electron going to get forced? Down. And what will happen is it's going to get forced down, and it's almost like this thing right here has a radius to it. Does that make sense? Because it's going to get forced down in like a circular pattern. That makes sense? Like as it gets forced down, it's not going to get forced down in a linear direction. It'll get forced down in like a circular pattern. So it'll actually look something more like this. It'll start getting pulled down, a little further down, a little further down, a little further down, a little further down. And it's almost like there's a radius. Okay. So here's what can happen then. Your magnetic force can equal a circular force. And you might be asked to put formulas together like we did last semester. What's the formula for magnetic force then? Well, is this a wire or a charge? Okay, so that'll be a Q times a V times a B. And then what's the formula for centripetal force? It'll be mass times V squared over R. Bottom one where it says tin cans and candles. Thank you. Does that sound familiar, the whole MV squared over R thing? It's been a while. So my goal now is we want to solve for the radius. So how do you get radius by itself in all of this mess?
Can't you just like flip like R and then like the Q times B? Yeah. There you go.
There, that will get you a radius. Take your QVB, bring it down to the bottom, bring your radius up. One of these velocities, by the way, can cancel. So here's a formula for your radius. Mass times velocity over Q times B. By the way, I feel compelled to point something out. They could really mess with you. Mass times velocity is momentum, by the way. So they could really try to mess with you, and they could give you a momentum, a charge, and a b value, and you could be asked to solve for a radius, which is really nasty, because you might not be like, okay, how in the world do you combine momentum with this stuff? But fortunately, we don't need to do momentum in this example. What is the mass of an electron? 9.11 times 10 to the negative 31. The velocity was 238 times 10 to the 5. What's the charge of just a single electron?
Just one.
Good, like 1.6 to the minus 19. And we have the field strength because it's 113 to the 5. So it actually isn't that bad, but you just have to remember that you can put these two formulas together and then do a lot of rearranging. I got 1.19 to the negative 11. You got that too? So what this implies then is that this guy right here, I mean, it's not going to form like a really full circle or anything like that, right? But what's happening is it's getting deflected in like a circular path, and the radius of that circular path is 1.20 times 10 to the minus 11 meters. That would be like the radius of this thing as it goes in a circle. Or at least as it goes in like I don't know, like a quarter of a circle. Does that make sense? So what you could have is this guy would go through the field and then like almost take like a right-hand turn. Go around a corner. Does that make sense? Okay, last one. It's the exact same thing, only we're now using an alpha particle. Well, okay, it's not the exact same thing actually. If it's an alpha particle, which hand do you use that? Okay, so field is still going into the page. So hand towards. Flip your hand over. You know how I said you can tell when people are doing this because they're going to be like stupidly like manipulating their hands everywhere? So which way is the force going to deflect this guy? Up. Okay. What this one says here is determine the velocity needed so that the force of gravity, because gravity would pull you down, is balanced by the magnetic force.
Do we need to make it equal to the force of gravity?
Good, yeah. We need to make our magnetic force equal to the force of gravity so that this thing would go through flat. This is really similar, by the way, to the Millikan oil drop experiment. Hopefully you guys researched that. In the Millikan experiment, it was gravity equals electrostatic force. Here we're just trying to make gravity equal magnetic force. So Q times V times B would equal mg. So what are we looking for again? We're looking for velocity. So V equals mass times gravity over charge times field strength. We're looking for determine the velocity needed so that gravity balances out magnetic force and it can go in a straight line. So, anyone got the mass of an alpha particle?
6.65 times 10 to the negative 27.
Thank you. Times 10 to the negative 27. Gravity, probably 981. I'm assuming we're on Earth. Charge is 2 of the elementary charges. And field strength is the same as last time. I got 1.8 times 10 to the minus 12 meters per second. Fairly slow.
Yeah, that's.
That's really slow. By the way, I just randomly made up numbers, so I didn't actually go into this intending for it to be a certain value. That makes sense?
We just throw a direction on there.
The velocity would be going, I don't know, that way. Sure, right. So ideally what would happen is this thing would fall down due to gravity, but the magnetic field would push it upwards, and so that way it would go straight. That's what we're hoping for. Okay, summary. I'm going to talk about that last slide another day. I need you to know probably 3 main things. The first one was all of those different rules where you're manipulating your hands around. And those suck, because you got to figure out positive or negative. You got to know what your thumb is, what your fingers are, what your palm is. So that's the first thing. Second thing, you have to be able to use those 2 formulas that are given. On their own, they're very straightforward. Like really, there's 4 things. I give you 3 out of 4, you solve for the 4th one. Chances are, I would expect they're going to make those forces, though, equal to another force back from like the dynamics unit. So like your magnetic force might equal gravity, or your magnetic force might equal centripetal force. It's even possible that you could make your magnetic force equal your electric force, which was that like K Q1 Q2 over R squared thing. So long story short, be prepared to make that force value equivalent to other force values. That'd be the 3rd thing. Sound good? Okay, tomorrow's a work day. I'm not actually here tomorrow. Monday I've got 1 last set of notes, and then we're done our unit. Yeah.
So study this if you don't get it.
Okay, let me just find the schedule so you guys know what we're up to for the next little while. I have 5 minutes, I guess.
Oh, sorry. Thursday? Oh, this small. It is like this. Oh, yeah, grab
Okay, so here's the schedule going forward. Workday tomorrow. Try to finish your labs, please. Mark your assignment. It's on the clipboard there. Last lesson, we're going to talk about some of the applications of this stuff. One of which I put a slide on, but I didn't really talk about. Motors and generators are actually based on this sort of stuff. The idea of how you can use a moving magnet or a moving charge to manipulate fields. So we'll do that on Monday. Tuesday, I'm going to try to do a demo lab with lots of magnet stuff. We're going to actually try to test all of this. So I'm going to grab some wires, some compasses, some magnets, and we're just going to test and make sure that all these rules actually work. Hopefully they do. We'll do a couple of work days because you need some time to process this. You don't really have school next week Friday. You do, but you don't.
Really need to come.
Well, I can't tell you that, but the school is going down to the Empress to watch some films that day.
Is it all day?
All day.
Is it like what kind of Thursday?
It's that social justice film festival. Remember that one lady who always comes and talks about it at our assemblies?
Is there any chance of the original assembly?
So, can't tell you that.
I think I might do
Okay.
like pieces.
So I'm not going to give you guys another quiz for like another full week though, so you have some time to process this. But then we're going to make that like a test week. So it's going to be quiz Monday, a couple of days more for processing, and then Thursday will be another test, unit test. But the good reason behind that, and you have a 4-day long weekend.
Why?
Oh, good.
Yeah.
Don't ask why.
We have PD days on both of those days, so. Does that work? So our last lesson will be on Monday, and then we basically have like 2 weeks to finish like another lab, another assignment, another quiz, a unit test, and I'm going to throw a project in there too if you want. Okay, that's all I got. So I won't be here tomorrow, so I'd say I'll see you guys on Monday, but I teach you all again. So.
Yeah.
So.
Yeah, see you in camp.
See you in Chem.
We're going to Chem
What day?
tomorrow.
Tomorrow I've got a video lesson I'm going to give you guys.
What about today?
Also a lesson.